This is the 200,000-pound thrust H-1 engine system 7055, disassembled into its major components prior to extensive component leak and functional checks. This outboard engine, together with inboard engine number 4055, has successfully completed qualification testing during this quarter. In this program, the H-1 engine system demonstrated that it meets all NASA requirements for safe and satisfactory operation at the 200,000-pound thrust level. The two engines were manufactured at Rocketdyne's Neosho, Missouri facility. The outboard engine was 10th in the production line of the 200K model, and the inboard engine was the 12th in its series. Each engine completed 3 production acceptance tests at Neosho. They were then shipped to Rocketdyne's Propulsion Field Laboratory in California, where the qualification test program was conducted. Engine 4055 accumulated a total of 2,081 seconds of main stage time in 17 tests, and engine 7055 accumulated 2,500 seconds in 34 tests. These tests ranged from routine operation to programmed malfunctions. 10 duration tests were made on each engine to demonstrate engine life and performance repeatability. 2 tests were made during which the outboard engine was gimbaled through a half angle of 3 1/2 degrees, the maximum angle being limited by the facility. The high and low temperature environmental tests were conducted on the Canyon 2 test stand. Internal engine temperatures of 130 degrees on the high side and 0 degrees on the low were established by exposing the engine system to those temperatures for 6 hours prior to engine start. In the safety limits series, programmed malfunctions such as failure of valves to open or close and variations in pump inlet pressures and electrical system voltages resulted in either safe engine shutdown or satisfactory operation. To demonstrate the dynamic stability of the combustion process of the H-1 engine, as shown here in high-speed photography, a 50-grain bomb was detonated in a baffle compartment of the injector to induce combustion instability. Stable combustion was re-established within 20 milliseconds of bomb detonation. Humidity tests on engine 4055 were conducted in an environmental chamber at Rocketdyne's Canoga facility. The H-1 was subjected to 3 days of 130 degrees temperature and 95% relative humidity. The C-clamp, used here to hold a thermocouple in place, gives an indication of normal rusting that might be expected under these conditions. The engine system itself, however, was virtually rust-free. H-1 engine 7055 was subjected to a decontamination procedure. It was rotated and held in various positions, then drained. The quantity of fluids remaining in the system at disassembly determined the effectiveness of the decontamination procedure. Static leakage tests were performed on the H-1 engine system prior to the start of the qualification program and upon completion of the test series. All fluid systems were tested for leakage while pressurized with GN2 at normal checkout pressures. Following engine disassembly, each component was given a leak and functional test to demonstrate the specified operating and functional characteristics. These tests were followed by a complete disassembly of each component for physical inspection and display. As the report period ended, component engineering evaluations were being prepared for incorporation into the final 200K H-1 engine qualification report. All requirements of the qualification program were successfully accomplished. The reliability demonstration program was completed with testing of the qualification engines. Based on a demonstration sample of 333 pre-declared tests, a reliability of .9946 at 50% confidence was achieved. Completion of the component qualification program was also attained during this report period. The last of 8 components to be tested in this program was the main LOX valve, which is observed during vibration test at cryogenic temperatures. During this test series, The valve was vibrated in each of the 3 axes for a resonant search. This was followed by a 10-minute sinusoidal sweep to 26 Gs and a random dwell for 5 minutes. Tests on the lock's bellows seal were also completed during this report period. These tests were part of an overall program to evaluate the seal and its operating environment. The tests were initiated as a result of the failure of the seal to perform satisfactorily at the 200 K level after having performed successfully at 188 K. Since the failures experienced were fatigue failures, it was felt that a resonant condition between seal cavity environment and bellows natural frequency may have existed. Results of the vibration tests and seal cavity environment studies indicate that the failures are not due to resonant condition. Studies on this problem are continuing. Another significant program during this quarter was the limits test study. Essentially, this consisted of operating the 200,000-pound thrust H-1 engine system at thrust levels up to 230,000 pounds. Purpose was to study the upper operating limits of the H-1 engine. The majority of the components used were from the 200K production line. However, certain hardware known to be marginal at the high thrust levels were modified. Engine HL-138 was instrumented with 92 strain gauges and 34 thermocouples. It was hot-fired for approximately 2,500 seconds in 25 starts. Evaluation of test data is in progress. Following final system and component leak and functional checks, the engine was disassembled for a thorough inspection. At the exit end of the thrust chamber, ripple patterns were noted. These were expected and are a result of thermal buckling at the higher thrust levels. Moderate damage was sustained in one area from a fragment of the 50-grain bomb used in the stability test. In the combustion chamber, a number of dents and 2 pinhole leaks were observed. These also are believed to have been caused by bomb fragments. The injector used in the limits test program was of standard 200K design, but modified to enlarge the orifices on the oxidizer side by 13% and on the fuel side by 10%. This allowed greater propellant flow with a minimum increase of the pump requirements. A hole was machined for installation of the 50-grain bomb. The turbopump was found to be in excellent condition following the limits test program. The A pinion, the intermediate gear, and the main shaft spline of the gear case showed little wear on the contacting surfaces. Bearings numbers 1 through 6 showed no excessive axial load resulting from increased power operation. Also, there was very little evidence of outer race outboard shoulder wear. Bearing number 7 of the turbine assembly was in excellent condition. Bearing number 8, also of the turbine assembly, was in good condition. Turbine wheels were binocular inspected, and there was no evidence of erosion or cracks on the turbine blades. The operating parts of the main LOX valve showed no unusual wear. The wear band on the gate drive shaft is normal for thrust levels sustained by this engine. The bearing race of both the drive shaft and of the idler shaft showed no evidence of galling. The rollers were in good condition and showed no signs of end wear. An improvement was made in the fit-up prior to weld of the bellows to the liner of the turbine exhaust hood. Post-test inspection showed no cracks as a result of engine operation as high as 230 K. The gas generator combustor body was fabricated from Hastelloy C instead of 347 steel. In addition, it employed an extra stud to permit more even distribution of flange and seal loading. Inspection showed the unit to be in excellent condition following the test program. The gas generator injector was a standard model with increased orifice sizes to provide for more propellant flow with a minimum increase in feed pressure. As noted by the carbon area, the condition of the injector was typical of those tested at 200 K. In general, the limits test engine HL-138 exhibited very satisfactory performance and provided data needed to calculate stress margins at the high thrust levels. A second limits test engine, HL-139, is currently undergoing test. This engine is instrumented with 13 accelerometers to provide vibration data on critical components. The program to evaluate an experimental thick-walled tube forming process continued during this quarter. In the conventional method, the die in which tubes are formed is machined from a steel plate. This method ensures a high degree of integrity, but requires a long lead time in fabrication before a new tube design can be evaluated. In the new process, a moderately wide trench is formed through rough machining of the metal plate. The contour is approximately that of the desired configuration, which in this case is an experimental thick-wall round tube. The cavity is filled with an epoxy resin. This filler cures and hardens at room temperature in approximately 12 hours. It will withstand 25,000 psi compressive stress. The mold in which the tube is formed can be made either by pouring the epoxy around a master tube set in place, or by pressing the tube into the mixture prior to hardening. Initial evaluation was concerned with dimensional integrity of the die, precision repeatability, and durability of the mold. Integrity and repeatability were very satisfactory. Durability, however, was not satisfactory, as wear was noted at the die throat after forming of the first 300 tubes. The first thrust chamber to be fabricated from tubes formed by this process had completed both furnace braze cycles as the quarter ended. It was then shipped to Neosho for completion. Durability of the die will continue to be evaluated during forming of tubes for a second thrust chamber. Accomplishments during this quarter were significant. Completion of the 200K engine qualification program, completion of the component qualification program, demonstration of 99% reliability at 50% confidence, and accumulation of data during successful testing at high thrust levels.